This presentation is on location planning. There's a lot of factors that a company should consider or might consider in location planning, such as proximity to customers, proximity to raw materials, quality of life issues, tax issues, etc. One important consideration that often looms fairly large is transportation costs, minimizing the cost of transporting materials that are inbound, raw materials if I'm a manufacturer, or goods for resale if I'm operating a retail distribution center or something like that, or outbound transportation costs, shipping my product out to my customers, whether they're consumers or whether they're other businesses. And there's two tools that we'll talk about to help solve this type of location problem, the distance load model and the center of gravity model. And again, both these models are appropriate when one of our objectives is to minimize transportation costs. That might not be an important objective in some facility location decisions, and if that's not an important objective, then these aren't the best tools to use. Okay, so the first tool that we'll talk about is called the distance load model, and the best way to understand these tools is with examples, so let's just work through an example. This company, Matrix Manufacturing, is considering where to locate a warehouse. It's got 4 stores in Ohio. You can see the locations of the different stores here, and it's considering 2 sites for the distribution center, Mansfield, Ohio, and Springfield, Ohio. And we'll show how to use the distance load model to make this decision. The way we make this decision is we do one analysis for Mansfield and we do one analysis for Springfield. If we were dealing with 3 different potential sites, we do 3 different analyses. So for one of the sites, let's say it's Mansfield, the first thing that we do is we make a list of the 4 stores, and then for each store we take the distance to the site, in other words the distance between the store and Mansfield, and we multiply that times the transportation load or the transportation volume between the site and the store. So one way to capture transportation load would be what the number of truckloads that we anticipate are going to have to go between the distribution center and the store every week or every month. We could also use pounds of material or some other measure besides truckloads. Then we add up the total. We add up those 4 products, and then we do the same thing for the other sites that we're considering, and we just see which site has the lowest total, the lowest sum. In other words, the lowest distance times load. We don't want to look at just distance. We don't want to minimize just the distance, the total distance between that we'll have to travel, because it's also important to take into account how many truckloads are going to have to go to each city. There may be a lot of truckloads that have to go to Cleveland and not very many truckloads that have to go to Dayton, in which case that would argue for a site that's maybe a little bit closer to Cleveland, a little bit further away from Dayton. So it's not enough just to look at distance. We need to look at distance times load. Okay, so let's assume that we know the distance. One way to compute the distance is to use XY coordinates, but there's a lot of other ways to get distances. We could use a ruler on a map, or in today's environment it's fairly easy to estimate them using a computer tool such as MapQuest, and it'll tell you the distance, and it'll even tell you the distance along roads, which is the way these trucks are probably going to have to travel. We might also be able to estimate rail distances and things like that if we were interested in rail transportation. So at any rate, let's assume that we've got the distances as an input to this problem. So there's 20.5 miles between Cleveland and Springfield, 4.5 miles between Columbus and Springfield, and so on. We might need to actually multiply these distances by 10. And again, for each city, what we do is we multiply the load times the distance. So if you take 15 times 20.5, you'll get 307.5, etc. We add those up, and the total load distance is 456.5. We do the same thing for Mansfield. So the distance between Mansfield and Cleveland is 8, and then we multiply that by the load, and we get 120, and so on. Add those up, and then we compare the two. The load distance for Springfield is 456. the load distance for Mansfield is 504, so to the extent that minimizing transportation costs is our objective, Springfield is going to give us a little bit better performance. Notice that the loads are exactly the same, because either way we anticipate the same number of truckloads coming into Cleveland, Columbus, and so on. The only thing that's really different here are the distances. Okay, the other tool is called the center of gravity method, and this is a very similar tool. We're basically doing the same thing. We're taking distances and we're weighting them by anticipated transportation volume, but with center of gravity method, we're not evaluating two different or a number of existing locations. The center of gravity is going to give us the one optimal location. So let's say that we want to locate a distribution center. Again, we want to minimize the transportation costs inbound to the distribution center, and we're assuming that just like we did in the previous problem, that cost is a function of distance. Cost and distance are related. So the question is, where is the optimal, where is the absolute best location? Instead of evaluating 2 or 3 different locations, we're asking, okay, where's the perfect place to put this distribution center? The way we use the center of gravity method is we superimpose a grid, an XY coordinate system, over the map. So we've got 4 suppliers here, and this is the way they would lay out on a map. And we're superimposing a grid system on the map, and we're just kind of arbitrarily saying that Portland is 0, 0 on the map. So we can see by looking at this grid system that supplier C is about 275 miles above to the north of Portland, and about maybe 110, 120 miles. No, I'm sorry, about 50 miles to the east of Portland. So we can coordinate, or we can compute, or we can estimate an XY location for each one of these suppliers. So again, for C it would be about 50 on the X coordinate and about 275 on the Y coordinate. We can do the same thing for each of the other suppliers. So I've just simply captured that information on the table here. I've put in the X coordinate for each supplier and the Y coordinate for each supplier. And the other thing that I've put in is the anticipated truckload volume. This is the anticipated number of truckloads we're going to need from supplier C, and so on. So now with this information, I can figure out the optimal X coordinate and the optimal Y coordinate. And of course, if I put those two together, that's going to tell me the optimal place on the map to locate this distribution center. So here I'm just going to determine the X coordinate. We'll do a separate calculation for the Y coordinate. So here in the left hand 2 columns, we've got the same information that we had on our previous table. And what we do is very straightforward. We just multiply each X coordinate, or each supplier's X coordinate, times the number of truckloads that we're planning for that supplier, and we note that product, and then we just add up the products. That gives us, in this case, 34,560, and then we divide by the number of truckloads. I've done that down here, and if you do that, you'll see that you get 323. Again, 323 is the optimal X coordinate, so 323 miles to the east of Portland. Now we determine the Y coordinate. We do the exact same thing. The only thing that's different in this table is we've got the Y data instead of the X data. And again, we multiply them together, so 290 times 13 gives us 3770. We add those up. We divide by the truckloads. Truckload is the same as it was in the previous computation. And if you do the math on that, you'll see that you get 172. So that's our Y coordinate, 172 miles north of Portland. So the optimal location, again, is 323 miles to the east of Portland and 172 miles to the north of Portland. We can't locate probably exactly in that location. It may be in the middle of some farmer's field or on a mountaintop or something like that. It's probably not on a road or a highway that we'd want to be located on, but that's going to tell us the best place, and we could probably get close to the best place, and we might need to also kind of balance this out with other other considerations that we might have in our facility location decision, like unemployment level, taxes, things like that in particular localities. Let's just look at the map one more time. We said that the optimal location was right about here, and that should make sense to you if you go back and you look at the table. You can see that this is not the distance or not the location that minimizes the total distance between the suppliers. The location that minimizes the total distance would be more towards the middle of the map. It would be somewhere like here. But remember, we're weighting this by transportation volume, and if you look at the transportation volume for supplier S, supplier sigma, you'll see that transportation volume is really, really high. So that kind of skews, our optimal location over towards supplier S just a little bit. So the distance load model and the center of gravity model are two good tools to use for facility location decisions, to the extent that minimizing transportation costs are an objective in the facility location decision. We can combine inbound and outbound traffic analysis. We can use other measures besides truckloads. These are fairly basic examples just to teach you the principles, but it should be pretty clear that you could extend these to more complicated situations. Let's talk for a minute at the conceptual level about types of businesses that tend to locate near customers versus those that tend to locate near supply or sources of supply. In many businesses, one of these types of considerations is really going to dominate in the location decision. Companies that tend to locate near sources of supply are companies where the inbound transportation is costly relative to outbound transportation. For example, if the manufacturing process subtracts weight to the material during the process. So if we're taking oranges and removing all the water and creating an orange juice concentrate, we will probably want to locate near those oranges because we're taking out a lot of the weight out of the product. It's going to be more expensive to do the inbound transportation than the outbound transportation on that product. Or it may be the case that the inbound product requires more refrigeration or more special handling than the outbound product. It may also be the case that the inbound materials are fairly bulky relative to their value. For example, if we're taking something like logs, logs are not rectilinear. You can't fit very many of them on a truck, and if you're converting those into kiln-dried lumber, what you're producing is going to have a much higher ratio of the dollar value to the bulk. So it's going to be less expensive to transport with respect to what the material's worth. So in that situation, we'll tend to locate near the trees to minimize the distance that we have to transport the unsawn, undried logs. On the other hand, businesses that tend to locate near customers tend to be situations where the outbound transportation is costly, basically the flip side of what we've been talking about. Maybe a situation where weight is added during the manufacturing process. So if I'm taking Coca-Cola syrup and I'm mixing it with water, I'm going to tend to want to do that near my customers because I'm adding all that water and as a result adding all that transportation cost to the product. It may also be the case that the outbound product requires special handling where the inbound product does not. For example, a bakery makes stuff that's fairly delicate, it's fairly perishable, it's fairly bulky relative to what it's worth. So a bakery is going to tend to locate near its customers, especially when we consider the fact that most of the things that a bakery receives, it's going to receive things like flour and sugar and stuff like that in bulk, and that stuff is fairly inexpensive to transport. So it doesn't cost very much to transport the inbound materials relative to the outbound materials.